Hello friends, welcome to chemistry classes by Vijay Kumar Sethi, class 11th chemistry, unit 6 thermodynamics, and in this video we will discuss about spontaneous process, criterion for spontaneity, that is driving force for spontaneous process, and entropy. First come to the spontaneous process. A spontaneous process is one that occurs on its own or once started proceeds without the external input of energy. It cannot be reversed on its own. If we want to reverse it, we have to supply the energy from external source. It is unidirectional. All natural processes are spontaneous. For example, a gas expanding to fill the available volume. Burning carbon in dioxygen giving carbon dioxide. Once we initiate this burning of carbon, this will continue till the complete consumption of carbon. Rolling of ball downhill. Rusting of iron. Freezing of water at temperatures below 0 degrees Celsius. And melting of ice. All these are the spontaneous process. They proceed in only one direction. That is unidirectional. You can also see in this diagram, this is the expanding of gas. Clear? This is spontaneous, but opposite of this is non-spontaneous. This diagram represents the rolling of ball downhill. This is a spontaneous process. Rusting. Okay, this is spontaneous and exothermic process. Ice melting. This is spontaneous and this is endothermic process. Now see, actually dissolution of sugar into tea or coffee or into water, this is also the spontaneous process. But if you want to remove the sugar from a cup of coffee, this is a non-spontaneous process. Okay. Now question arises, why these spontaneous processes proceed in only one direction? What is the criterion for this? What is the driving force for spontaneous process? Okay, that's why we will discuss criterion for spontaneity or driving force for spontaneous process. First we will discuss the one criterion, that is a decrease in enthalpy. Again consider the spontaneous physical process like flow of water downhill, fall of a stone onto the ground. Now if we compare the energy of these processes in the final state, we will observe that there is a net decrease in potential energy in the direction of change. Clear? In the same way, flow of heat from higher temperature to lower temperature, that is also the spontaneous process. Now consider some chemical reactions. This is the formation of ammonia and this is an exothermic process. Exothermic process means energy is released. That is, the energy of the products formed is lower compared to the energies of the reactants. In the same way, this is formation of HCl. This is an exothermic process. This is formation of water. This is again exothermic process. Exothermic chemical reactions are spontaneous because decrease in energy has taken place. From all these, we can conclude that driving force for a spontaneous process is a decrease in energy or enthalpy, that is negative of delta H, negative enthalpy. Clear? This is one criteria to decide the spontaneity of a process. But now, examine the following reactions. The reaction between solid barium hydroxide octahydrate and solid ammonium thiocyanate is endothermic, but this is spontaneous. Clear? Now endothermic means this is absorbing heat. The energy of the product is more. Still this is spontaneous. While most acid-base reactions are exothermic, the reactions of baking soda with vinegar is endothermic, but still this is spontaneous. Dissolution of common salt into water is endothermic and spontaneous. Okay. These reactions to endothermic, that is delta H is positive, are spontaneous. Therefore, it is concluded that decrease in enthalpy may be a contributory factor for spontaneity, but it is not true for all cases. That's why we can say only Negative delta H is not only the criteria to decide the spontaneity of a process. There is also the one more criteria. Now what is this? We will discuss the another criteria. Now examine such a case in which delta H is 0. That is, there is no change in enthalpy, but still the process is spontaneous. And its example is diffusion of two gases into each other in a closed container which is isolated from the surroundings. That is, we are discussing one isolated system, diffusion of two gases. Now see this diagram. In this gas, molecules of gas A are there. In this compartment, molecules of gas B are there, and both are separated by this stopcock. Okay. Now, if we pick up from this container, definitely we will get the molecule of gas A. In the same way, if we pick up from this part, again we can say it will be the molecule of gas B. Now, open this stopcock. Okay, stopcock is opened. Now we will get this situation. Diffusion of gases will taking place. Gas A will diffuse into this compartment and gas B will diffuse in this compartment. Now if we pick up from this one, then we are not sure that it may be molecule of gas A or molecule of gas B. Clear? We can say that the system has become less predictable or more chaotic. Is it clear? We may now formulate another postulate. In an isolated system, remember, in an isolated system, there is always a tendency for the system's energy to become more disordered or chaotic, and this could be a criterion for spontaneous change. That is, we can say that is a disorderedness may be another criteria. And to express this disorder of system, another thermodynamic term is used, which is called entropy. Now, what is this entropy? This is represented as capital S. Entropy is a measure of the degree of randomness or disorder in the system. The greater the disorder in an isolated system, the higher is the entropy. Qualitatively, this is the order of entropy. That is, in solid, lowest entropy, and in the gas, highest entropy. That is, in gas molecule, this order is maximum. That's why highest entropy. Entropy is a state function, and this change in entropy is independent of path. Whenever heat is added to the system, remember, heat is added to the system, it increases molecular motions, causing increased randomness in the system. Okay, that's why we can say a system at higher temperature has greater randomness in it than one at lower temperature. That is, at higher temperature, entropy is more, and at the lower temperature, entropy is less. Heat added to a system at lower temperature causes greater randomness than when the same quantity of heat is added to it at a higher temperature. Clear? This suggests that entropy change, remember again, entropy change is inversely proportional to the temperature. Now, again, two things we are considering which are opposite to each other. We are saying at higher temperature, randomness is more. But another, at the same time, we are saying entropy change is inversely proportional to temperature. Clear? Actually, when we consider the absolute value of entropy, it depends on the temperature. Higher the temperature, more the entropy. But if we consider the entropy change, clear? If we consider the entropy change, then this is inversely proportional to the temperature. Why? Because at lower temperature, greater randomness is there. But at the same quantity of heat is added to it at higher temperature, randomness becomes less. Okay, and that's why quantitatively we can relate the heat and temperature like this. Delta S is related with Q and T for a reversible reaction as this. Change in entropy is equal to Q reversible divided by T. Now, the total entropy change, that is delta S total for the system and surroundings of a spontaneous process, is given by delta S total is equal to delta S system plus delta S surrounding, and this is greater than 0, that is always positive. Okay, we can see actually if we consider the only isolated system, its entropy is always positive. But if we consider the open system and closed system, we have to consider the entropy change of system as well as entropy change of surrounding. That is known as delta S total. When a system is in equilibrium, the entropy is maximum. That is randomness is maximum, and the change in entropy, that is delta S, is 0. Okay. Entropy for a spontaneous process increases till it reaches maximum, and at equilibrium the change in entropy is 0. Okay. Now this concept of entropy or randomness you can also explain, or you can also understand by taking the classroom situation. When classes are continuously going on, teacher is coming to the class and you are studying. Okay, everything is systematic. You are sitting at your places. But as soon as the bell of recess is ringing, what happens? What happens? Everyone gets the disorderliness. Every student go to the toilet, opening their tiffin, taking the tiffin. Teacher is also going to the staff room. That is, disorder is increased or randomness is increased. But after the certain time, after the 10 to 15 minutes, maximum randomness is there, maximum entropy is there. Okay, and at that situation, change in entropy is 0. Since entropy is a state property, we can calculate the change in entropy of a reversible process by this. Delta S system is equal to Q system reversible divided by T. Now, both for reversible and irreversible expansion for an ideal gas, this we have discussed in the one of my previous video. Okay, under isothermal conditions, delta U is equal to 0. That is for isothermal condition. For reversible and irreversible expansion for an ideal gas, internal energy change is 0. But delta S total, that is sum of delta S system and delta S surrounding, is not 0 for irreversible process. Delta S total is 0 for reversible process at equilibrium, but irreversible process it is not 0. Thus we can say delta U does not discriminate between reversible and irreversible process, whereas delta S does. Okay. Now on the basis of delta S total, or we can say change in entropy, we can predict the spontaneity of the process. If delta S total is greater than 0, that is positive, process is spontaneous. If delta S total is less than 0, that is negative, process is non-spontaneous. If delta S total is 0, we can say system is in equilibrium. But again remember, we are considering delta S total, that is sum of delta S system and delta S surrounding. It means delta S system alone cannot decide the spontaneity of the process for closed and open system. We have to consider the delta S of surroundings. Clear? That's why we can say neither decrease in enthalpy, that is negative delta H, or increase in entropy, that is positive delta S of the system alone, can determine the direction of spontaneous change for closed and open system. That's why we have to consider both the criteria. And when we consider both the criteria, we will get another thermodynamic property that is known as Gibbs energy. And about this Gibbs energy, we will discuss in the next video. Subscribe my channel to get the next videos of this chapter. Thank you.